All right, I'm going to go over the chapter 4 test questions. First one I thought was going to be pretty straightforward, just a 2D problem. We got this rig here holding it's 5 kilonewton rig, and it shows the weight of the rig acting at this point right here, center of gravity. And it's welded to this vertical beam, which is embedded in concrete at point E. The weight of the rig acts through the center of gravity, 2 meters to the left of this DBC beam. The rig is raising a 15 kilonewton crate, 3.5 meters away from the vertical member, right here. And the tension in the wire, this wire right here, CF, is 18 kilonewtons. So the first part was just to draw a complete and correct free body diagram. So I did that right here. And I was looking for, at the minimum, 4 dimensions. So this one has all the dimensions on it in terms of, what you need to know to sort of recreate the entire diagram. But I've got all the dimensions I need, going from, again, points that the forces are acting to, the reference points on the assembly. Down here at the bottom, I have reaction forces. This is embedded in concrete. So there are 3 reactions. There are the forces in the X and Y direction. In other words, if you took this thing and grabbed it and tried to push it left or right or pull it up and down, it wouldn't move, right? There's reaction forces preventing that from happening. And those reactions are generated by the fact that this is embedded in concrete. Also, you can't come up to this and push it and cause it to swivel about E, right? So there's a moment resisting rotation at E. And I drew my moment counterclockwise in the positive direction. And then, of course, I have my applied loads. So these two are pretty straightforward. I have a 15 kilonewton load, 5 kilonewton weight. This is the one where people seem to have some issues with. This is an 18 kilonewton force acting on the structure. So when you draw a free body diagram, you're looking and saying, how do I separate the structure of interest from the rest of the world? So you would separate it here and here, right? You replace these, you always replace chords with tension vectors that are acting away from the body. And then down here, we replace the connection point with a moment and 2 forces. So that's the free body diagram. Part B is to calculate the reactions at the fixed support E. Report magnitude and direction for each reaction. So I was expecting magnitudes and directions. And I was also expecting units. So let's look at the first part of this. So the first part is sum of the forces in X is equal to 0. All we have are EX, right? All the other forces are in the Y direction. Right? There's no other Y direction forces. So the sum of the forces in X is equal to 0, so EX equals 0. Next, we have the sum of the forces in the Y direction is equal to 0. So in the Y direction, we've got E sub Y, that force acting up the way I drew it. We've got 15 kilonewtons and 5 kilonewtons acting down, so those are negative signs. And of course, we have the 18 kilonewton force also acting down. You do the math, negative 20 plus negative 18, you wind up with 38 kilonewtons. E sub Y is a positive value, right? Negative, bring it to the other side, you get positive, 38 kilonewtons up. All right, some of the moments. Some of the moments about E equal to 0. So this is looking at how are all the forces generating moments. Now, I could have taken any point on this structure and chose that to do the moments about, right? Some points are easier than others. For example, I could have chosen point B, right? I could have chosen point A. In fact, for practice, you should sit down, write this out after you go through this and figure out, all right, how do I get the answer using some of the moments about point B? How do I get the answer using some of the moments about point C, right? Any point you take the moments about, the forces acting at that point are eliminated because they're essentially at 0 distance, right? So for example, EX and EY, if some of the moments about E is going to be equal to 0, in fact, I probably should have labeled these on my diagram, A, B, C, D, E. But first we have an actual moment at E, right? This is what we don't know. We don't know the moment. This is being generated at E. Then we have the 15 kilonewton force is generating a counterclockwise moment. In other words, if this thing were free to rotate about point E, right, this force would cause it to rotate counterclockwise. So counterclockwise forces are positive. In fact, I'll put a little arrow here. So 15 Newton force or kilonewton force, it's positive because it's generating a counterclockwise moment, and it's acting at 3.5 meters away from point E, perpendicular distance. Again, the 5 kilonewton force also generating a counterclockwise moment. So that's a positive moment, 5 kilonewtons times 2 meters, perpendicular distance. Next, we have an 18 kilonewton force, right? This is generating a clockwise moment. So this force is acting to generate a clockwise moment. So that's going to be a negative sign. And it's 18 kilonewtons acting 1 meter away as your perpendicular distance. You basically just multiply these values together. You wind up with the moment about E is negative 44.5 kilonewton meters. Now, I drew my moment counterclockwise, right? My answer came out negative. If you had drawn your moment clockwise, you would have had a negative sign here, right? Because clockwise is negative, and then it would have come out positive. The sign tells me, oh, I chose the wrong direction. So the moment is 44.5 kilonewton meters, and it's in the other direction. So I'm reporting all the values down here. E sub x is 0. These are the reactions, right? E sub y is 38 kilonewtons. Notice the up arrow indicating it's acting up, positive y direction. And the moment about E, or the moment at E in this case, 44.5 kilonewton meters. Again, notice the units. A moment is a force times a distance, and the direction, clockwise. All right, so that's number 1. All right, let's go to the second problem. So the second problem, actually, before we do that, let me just quickly show you, if number 1 looked kind of familiar, very familiar, very similar to the one we did in class for practice, where we actually looked and said, all right, which one is the correct free body diagram, right? And again, we chose free body diagram B, right? Notice the chord here, we've got a tension vector, and we've got our reactions, 2 forces, and a moment at E. So that was right from the notes. Essentially, it's a pretty similar problem. All right, let's see. Problem number 2. Let me show you real quick. This was pretty similar to one of the homework problems. Let's see. Let me see if I can find it. I'm going to pause the video. All right, so this is problem 4.110. This is a little more complicated problem. We've got a boom, and we've got 3 tension cords, right? So that problem is a homework problem. Additionally, this is not too much different from this problem with the supporting of the plates of uniform density, right? Instead of a plate, we have a boom, right? So the plate, we have the weight of the plate. In our problem in the test, we had a force acting off of the boom. So again, not too different. The problem I gave you here was pretty nice because there was some symmetry going on. The first thing I did is I went in and drew myself some tension vectors acting from B to E and B to D. I also looked at the joint here. It's a ball and socket joint, so there's no moments. There's only reaction forces because a ball and socket joint is free to swivel, right? You can swivel about that point. So there's no prevention of swiveling, so there's no reaction moments. But there are reaction forces. You can't take this and move it up or along any of the axes, right? There's a reaction to that stuck in the ball joint. All right, so there's we look at this and we try to do some of the forces in, say, X, for example. We'd have 2 unknowns, right? We don't know the X component here, and we don't know the X components of either of these tensions. So really 3 unknowns. same in the y, same in the z, right? These tension vectors act in the x direction, the negative x direction, the positive y direction, and one in the positive z, one in the negative z. So we're going to do some of the moments first. And I chose to do some of the moments about A, and let me show you what I've written here. Way back, we learned about moments, right, of a vector, a force vector, acting on a point about a certain point. So for example, the moment about A, there are three different forces generating moments. We've got the weight and these two tensions in the lines, right? So let's start with tension BD, right? Tension BD, we have the position vector of B with respect to A, right? So B, the point where the force is acting, or the point on the line of action of the force, and A, the point at which we're interested in the moment about. So position vector of B with respect to A crossed with the force, right, which is the tension vector in this case. Then we've got the same thing for tension vector BE, right? Again, position vector of B with respect to A, TBE, cross with TBE. And finally, we've got the weight vector. So this weight is pointing straight down. It's 4 kilonewtons, and it's acting at C. So we got the position vector of C with respect to A. All right, so the first thing I did is I started to develop my tension vectors. And the tension vectors are, again, just, taking your final minus initial points. Now, I did this sort of, one point at a time, but you can see here that we've got we can look at the tension vector also as which direction are we going? How do we get from B to E, right? So to get from B to E, we got to go -4 in the I direction, right? Backwards. Then we got to go +7 in the J direction, right? 7 meters. And then B to D is over here, +4 in the Z direction, right? And if you take the square root of the sum of the squares of these coefficients, you get 9. Right, so let's just do that real quick. Square root of, let's see, 16, what are the numbers? 16 plus 16 plus 49, right? We get 9. All right. Tension vector BE, this is basically the same vector, right? It runs the other direction. So we go from B to E, we go -4 in the X direction. Then we go +7 in the Y direction. And then we go -4 in the Z direction, right? This is going backwards along -Z. And again, divided by the magnitude 9. The tension vectors are all in kilonewtons. And notice, this is the magnitude of the tension vector. These are the unit vectors, right? Lambda, unit vector. So I gave you the general formula right here for how to find the tension vectors. I also gave you the general formula for the moment about a point. Right? All right, so let's figure out R's and W. Well, W is just the force -4 J kilonewtons, right? It's acting in the -J direction with a magnitude of 4 kilonewtons. And then we've got the position vectors. Position vector of B with respect to A is 4I, right? And the position vector of C with respect to A is 7I, right? 7, these are all meters. All right, so now we can start doing some math. So basically, I just started plugging things in. So I've got R of B with respect to A, which is 4I, crossed with the tension vector TBD. I pulled out the 9. I've got the top of the unit vector there. And I do the same thing for TBE, right? And of course, the weight vector. So I'm just setting up the cross products, right? So you can see here, R of C with respect to A crossed with the weight. Right, direction's important here. I also gave you up here the cross product information, right? So I cross J is K, I cross K is -J, K cross J is -I, and vice, et cetera, et cetera. Right? So you do the cross product and you wind up with something like this. Excuse me. Notice all the I cross I terms go away. You're left with just K's and J's for both of these tension vector cross products, and then we've got just a -28K over here. Then, because the sum of the moments is equal to 0, you can take all the J components and then all the K components and you can set them up. So the J components, you can set them all to 0. You add up the J components. We got negative 16 over 9 TBD plus 16 over 9 TBE equals 0. This equation tells you, yeah, TBE is equal to TBD. The tensions are equal, right? And the next equation is going to actually give you some information about that. So simplifying this a little bit, I've got, let's see, 28 over 9 TBD plus 28 over 9 TBE minus the 28. This is all the K direction. I wind up with TBD plus TBE is 28 times 9 over 28. Right? So we wind up finding out that these add up to 9. So TBD is just 2 TBD is 9, which gives you, go to the next page, TBD is 4.5 kilonewtons, TBE is 4.5 kilonewtons, right? They're both, whoops, they're both 4.5 kilonewtons because they're equal and they add up to 9. And I just replaced, in this case, I just replaced TBE with TBD. You wind up with 2 of them. All right. So now what we do is we go back and we can plug these tensions back into our equations, right? So we can have, plug in the tension TBD, plug in the tension TBE. We can actually solve and get a tension vector that has I, J, and K components that are actual numbers this time. And then what we do is we say, all right, the sum of all the forces in the I direction, the J direction, and the K direction are equal to 0. Well, let's do that. So sum of the forces is equal to 0. So we plug in our, again, we plug in our 4.5 kilonewtons to the TBD equation, right? This one right here. We'll wind up with, and the TBE equation, and then of course we have our weight equation. So again, plugging these values back into their vector form, right? Replacing the magnitude of the tension vectors, TBD and TBE, we'll wind up with now vectors for the tension in the lines, right? Notice these, there's no unknowns in here now, right? And now we say, all right, the sum of the forces in X is equal to 0. So we take all the I components. Remember, we still have A components. We don't know the A components. We don't know AX, AY, or AZ. So those are the unknowns. So AX minus 2I minus 2I equals 0. You find out AX is equal to 4 kilonewtons. It's in the positive direction. A sub Y. A sub Y is unknown. We drew it acting upwards, right? So I treated it as a positive. Notice all these are running along the positive direction of the axis. So they're all positive. At least that's how we're treating them. AY plus 3.5 plus 3.5 minus 4, right? These are all the forces in the Y direction due to the tensions and the weight. Notice in this case, AY is negative 3 kilonewtons. So we assumed AY is pointing up. We got a negative sign. AY is actually pointing down. And then finally, the Z direction, we've got A sub Z. Again, we assumed it's positive. We've got in the Z direction plus 2 and minus 2, right? So we find out AZ is equal to 0. And so finally, the answer in all its glory with all the units, the tension vectors are each 4.5 kilonewtons, right? We just wanted the magnitude of those. And the vector A, I asked for it in Cartesian coordinates. Report reaction A as a vector in Cartesian form. So this is the vector 4I minus 3J kilonewtons. So yeah, that's the test. Again, some of the problems should have looked familiar, especially if you did the homework and went through some of the in-class practice problems and the slides. I just wanted to show you real quick. Again, some of the in-class example problems were a little more complicated than this, right? In fact, we had this problem right here with 2 tension vectors and 1 weight and this pivot point, right? So fairly similar, just this one had a lot more restraints, moments about axes. And then the example problems I gave you for the test, not too different in terms of, in fact, very similar in terms of the concepts, right? We had a utility pole. We replaced the chords with tension vectors, right? We have down here, it's buried into the ground. We have reaction forces and a reaction moment, solving that. And then over here, we had a problem. I think I mentioned I would give you a problem very similar to this. In fact, this is essentially the problem that was on the test, except this is vertically oriented and the force is in multiple directions, right? It runs in the X, the negative X, positive Z, and negative Y direction. Whereas the force in the problem in the test was just acting in one direction. So it was much easier, right? This is also symmetric. So yeah, should have been pretty straightforward.